Hey physics kids, Campbell here. We're going to continue our discussion of electric fields by looking at uniform electric fields. Now remember I talked the other day in class about how parallel plates, which have equal but opposite charges, set up this beautiful uniform electric field. And it is the same everywhere in the between the plates, which is why I can't use that KQ over R squared equation, because whatever the electric field here is the same as the field here, which is the same as the field here. Now, parallel plates have some useful applications. Because that field is uniform, we can use parallel plates to accelerate particles. Now, the motion of a charged particle in a uniform electric field is very much like projectile motion. So moving particles in uniform gravitational fields, which is what we studied in AP Physics 1 last year. So if we think about placing a charge particle, and it has to be a charged particle, in an electric field, right, it's going to feel a force, and the magnitude of the force is given by our equation here, where the force is equal to the electric field times the magnitude of the charge that we put into the field. And once a charge feels a force, right, it begins to accelerate. And so we can use Newton's second law, the sum of the forces, or the net force, is equal to mass times acceleration, to determine the magnitude of the acceleration of the particle. And then we can use kinematics to find things about speed and time and distance. Yay! So first let's take a look at a charged particle that we put in the field, and it starts to move parallel to the field. This is kind of like free fall, because the direction of the force is in the same direction of the motion of the particle. So if we look at our uniform electric field here, which means it's constant in magnitude and direction, that means that the acceleration is constant, right? Because force is E times Q, and then if force is equal to MA, then all of those are constants. And we can use kinematics. And so now, a couple things about direction, right? Because if the charge is positive, the acceleration is going to be in the direction of the electric field. Remember, electric field lines were set based off the motion of a positive charge. So if the electric field, which points from the positive plate to the negative plate, the positive charge, if we put it in here, right, it's going to move toward the negative plate. Unless it's already at the negative plate, in which case it's not going to move. Or if we put a negative charge in here, right, remember that the negative charge is going to move in the opposite direction. It would move from the negative plate to the positive plate, which is in the opposite direction of the electric field. Well, remember, the electric field was just we needed a direction, right? It's a vector, and it was set based off the motion of a positive charge. So everything we do with electrons, we say that it's moving against the electric field, which it's, yes, by definition, but it's moving in the direction that it wants to move. Now, let's take a look at how we would do some calculations with this. So here is my setup here. My electric field points from positive to negative in between my plates, so it's pointing down in this picture. And I put a positive charge, which looks like it's a proton, right, because its charge is 1.6 times 10 to the negative 19. Nope, but it's got the mass of an electron, so maybe it's a positron. And I have an electric field strength of 2,000 Newton coulombs. A distance of the plate separation is 1 centimeter. So first thing I want to do is find the force on the charge. So we have one equation, right? It's that force is the electric field times the charge. So take the magnitude of the charge of your positron and multiply by 2,000, and you get 3.2 times 10 to the negative 16 newtons. Next question is to find the acceleration. Well, Newton's second law says that acceleration is the net force divided by the mass. So we're going to take our force here, we're going to divide by our mass, which is teeny tiny, and we get a huge acceleration. So 3.5 times 10 to the 14th meters per second squared. Well, now we could do all sorts of things, right? We can put that into kinematics and find things about speed or time. I already know some distance, but what if we want to find the speed when it hits the plate if it starts at rest? Well, what equation would you use? Well, there's acceleration, right? So you can't just do distance and time, but oh wait, I don't know anything about time. So how about this equation? Oops, let me move myself. There we go. V final squared equals V initial squared plus 2a delta x. Remember that one? Well, my initial velocity is 0, right? I have my acceleration and my distance is 1 centimeter. Just convert that to meters. So when we do our little math, all right, we get a very speedy particle, but it's teeny tiny, right? Which is why it accelerates so quickly. So let's look at another example of particles accelerating in uniform electric fields. In our last example, we looked at a particle that started at rest and moved in the direction of the electric field, or against if it was a negative charge. This time we're going to look at a particle that gets injected into an electric field that's perpendicular, initially anyways, to the direction of the electric field. So in this example with these plates, since this is the positive plate and this is the negative, right, the electric field line will point down, right, away from positive towards negative. But the electron, right, is feeling a force of attraction to these positive charges and repulsion from these negative charges. So as the particle moves in here, the force it feels is vertically up, which means that the particle is going to follow this parabolic path. This is just like projectile motion when you throw a ball near the earth, right? You throw the ball, if you throw it horizontally, right, what happens? Well, it makes a parabolic path down towards the earth because the earth, the acceleration due to gravity, is vertical. And in this example, because I put the plate this way, my acceleration is also vertical. So because this particle starts out with motion in the x direction, but my acceleration and my force is in the y direction, we're going to have to split what's going on in the x direction from the y direction. Now, in the y direction, that acceleration is constant, so we can use our kinematic equations. But because things are going on in 2 dimensions, we have to look at the x separate from the y. So in the x direction, right, there's no force this way. So the force is only in the vertical direction. So in our x direction, that means there is no force, which means there's no acceleration. So that means the velocity is constant, just like with projectile motion. So the only equation I have in the horizontal direction is that the change in position is equal to that constant velocity in the x times time. So that's, we rearrange that, right? That velocity is the change in position over change in time because I have constant velocity. Now, if you remember back to last year when we did projectile motion, a lot of times I'd ask you to find how far it goes, but I wouldn't give you the time. But that's okay because we have the y direction, right? And in the y direction, we do have acceleration and force. So all of my kinematic equations apply. Now, let's see how we would use this in a problem. So for this plate, I'm going to inject an electron. Right? An electron has a mass of 9.11 times 10 to the negative 31st kilograms and a charge of 1.6 times 10 to the negative 19th. And I'm going to inject it horizontally, so all the initial velocity is in the x direction, and its initial speed is 7.2 times 10 to the 6 meters per second. Speedy particle. I want to know, will it strike the plate, or will it exit the electric field? Well, in order to figure this out, right, we need to find out how far it travels in the x direction. If it travels less than 2 centimeters, it gets stuck, right? It sticks to the plate. But if it travels more, then it's going to leave the electric field. So what we're going to have to do first, right, is find out how long it takes, right? Because in the x direction, I only have the change of position is the velocity, which I know, times the time, which I don't know. So I need to go to the y direction first to figure out the time. See if you can remember how to do that. So pause the video and see if you can get this right. Does it leave the field or not? All right, well, the best way to do this is if we go to the whiteboard. So come on, let's go. So remember, acceleration is the net force over the mass. And our net force comes from the electric field, right? The electric field times charge divided by the mass. So now it's just a matter of plugging and chugging. We have our electric field of 2,000 Newton over coulombs. The charge on an electron is 1.6 times 10 to the negative 19th. Don't use the sign of the charge in our calculation. And we have the mass of an electron, which is 9.11 times 10 to the negative 31st kilograms. Now, if this looks at all familiar, it's because I picked the same numbers as we had in the last problem where we started at rest and just dropped between the plates. So that means our acceleration is the same value as it was last time, which is 3.5 times 10 to the 14th meters per second. Kind of convenient, huh? All right, so that's the acceleration. Now I need to find out how long it takes to go a distance. So from a kinematic standpoint, right, that would be this equation, y, my least favorite, y final equals y initial, plus the initial velocity in the y times the change in time plus 1/2 acceleration time squared. Now, if we start here, we'll call this the 0 point, which means my final position is that 0.15 centimeters, but make sure we put that in meters, so 0.0015. These are 0, and remember that it's coming in the x direction, which makes this term 0 as well. So that means that this is equal to 1/2 the acceleration, which is our number right here, 3.5 times 10 to the 14th t squared. And so now I just got to do some math. T is the square root of 2 times 0.0015 divided by our acceleration, 3.5 times 10 to the 14th. And so for time, you should have gotten the teeny tiny number of 2.9 times 10 to the negative 9 seconds. Don't blink. All right, now that I have my time, we can go to our x direction. Remember, in the x direction, the only equation I have is that delta x is the velocity in the x times time. Our velocity in the x of our speedy particle is 7.2 times 10 to the 6th times our time, which is very short, 2.9 times 10 to the negative 9 seconds. And what you should have found is this is 0.021 meters or 2.1 centimeters, which means no, it doesn't hit the plates. So our particle, right, it comes in, it feels a force, which causes it to move on a parabolic trajectory, and it exits right about there. How'd you do?
But wait! In that problem, we ignored the force of gravity on the electron. Why? Right? I mean, it's there. Well, if we think about the force of gravity on our electron, right, if we actually went and calculated it, the mass of our electron times 9.8, that's teeny tiny, right? Much smaller than the electric force. So when it is so small, and when we're dealing with small particles, we can ignore it. And that same thing is true for a proton.
Well, that's it for Forces and Fields. Fill out your WSQ, and I'll see you in class.